Hello everyone, and welcome back to another GIS lecture video. And this lecture video is going to be a slight tangent away from this idea of georeferencing by just giving a better definition of this idea of Euclidean distance. And again, if this is a review for you, by all means feel free to skip this video and continue on to talking about how we can improve accuracy. But if you're curious or have never seen Euclidean distance, I want to just briefly talk about it with a specific point of how it relates to the Pythagorean theorem. Okay, so let's go ahead and give ourselves plenty of space since this isn't really related to anything that we've talked about before. And let's go ahead and take our exact same example here. All right, so this is our example. This is our example of our error, right? And we said in the previous video that this distance along this black line here, that this distance was our error, and we want to be able to calculate that. So how do we calculate the distance between 2 points? Okay. And what I want to do before we talk about that is I want to draw an example of a right triangle. I'm going to try and get my lines a little straighter here. Right. So this is going to be a right triangle. Right. And we will call the hypotenuse of this right triangle, right, this is the hypotenuse. We'll call the hypotenuse of this right triangle A, and we'll say that this triangle has sides B and side C, right? And so if you know your Pythagorean theorem, you know that the value of A squared is equal to the value of B squared plus C squared, right? This right here, this is just the Pythagorean theorem. Right? Hopefully you learned this in high school or maybe early on in college math, that we can relate the three sides of a right triangle based on this equation, where A is the length of the hypotenuse, B is the length of the base, and C is the height. Okay? So what we can do here, using a little bit of basic algebra, is we can calculate the side of A, the length of A, by taking the square root of B squared and C squared, right? So just rearranging this Pythagorean theorem, we can get A is equal to the square root of B squared plus C squared, right? I didn't do anything other than just move this square by square rooting both sides, okay? That's all I did. So using this equation here, right, we can get the length of this hypotenuse, okay? So let's go back to our example here, where we have a green point, which I'm actually going to make blue just in case people are red-green colorblind. We have a blue point, and we have a red point, and then we have the length of a line that connects them, right? So this is me just redrawing this, okay? And so we learned from our discussion on projections that both of these points, right, the point where it should have been and the point where it actually ended up, we know that both of these points are on a projected coordinate system, which means, right, that they exist in an XY plane. That they exist in an XY plane. And so what that means here is that our point here has an X coordinate and a Y coordinate, right? And we'll call this x1, comma, y1, right? And we know that our point where it ended up also has a different coordinate, x2, comma, y2. Right, so again, all I've done is taken this idea that we're projecting this data set to prove that we've moved this data into an xy projection, where we have an x and a y associated with where it should have been, and we have an x and a y associated with where it ended up. Okay? So the magic happens when we think about what happens if we draw a horizontal line. I'm going to do this in purple. If we draw a horizontal line, so parallel to the x-axis through one point, and we draw a vertical line, right, so parallel to the y-axis through the second point, right? And then we make bold, right, everything from the point that the two lines intersect and the point that the 2 points we have, right? If I make that bold, what you might notice is that we've actually created ourselves a right triangle, right? We've created ourselves a right triangle. Where this right here and this point here, right, this is x2, this is x2 comma y2, this is x1 comma y1, right? So what's this? Well, think about that for a second. The x coordinate, right, of this is going to be x2, right? Because if we travel along the x-axis to get there, it's going to be the same distance along the x-axis as x2, right? And its y-coordinate, well, if we go up along the y-axis, it's going to have the same y-coordinate as the first point, y1, right? Okay. I'm going to slide over a little bit to give us some room here. And so we have a right triangle. Just throw that in there so that we know that we're still talking about a right triangle. We have three different sets of coordinates, x1, y1, x2, y2, and x2, y1, coming from our coordinate system here. But then we also have the side lengths coming from Pythagorean's theorem of right triangles. So we still have an A, a B, and a C. Okay. Well, now we can calculate C and B based on our coordinates, right? Because this length of C, right, think about this for a second. This length of C is going to be the distance from here to the distance here. That's what C is. C is the length of this line. Well, they share the same x coordinate, right, by definition. So the length of this line here is going to be equal to y2 minus y1, right? Again, the y-coordinate of this point minus the y-coordinate of that point is going to give us the length of the line between them, which, according to our Pythagorean theorem right triangle, we call C. We can apply the same logic here to B, right? The distance from here to here, right, in our Pythagorean theorem is B. Using our coordinates, right, they have the same y-coordinate, they're both y1. So the distance from here to here is going to be x2 minus x1. Right? Again, that's just the x-coordinate of this point minus the x-coordinate of that point. What you get is going to be the length of this side B. Okay? Well, we want the length of side A, right? Because the length of the hypotenuse, right, this side here, this is the length between the 2 points, right? This is the error. So this A, right, is our error, is our distance, right? And so we have an equation to calculate A based on B and C. So let's go ahead and rewrite this equation using our points here. So A, which I'm now going to call distance, right? And again, to remind everybody, this distance is the hypotenuse of the triangle. Sorry if I butcher how to spell hypotenuse of the triangle. Right, is going to be equal to B squared. Well, B squared is just x2 minus x1 quantity squared, right? Because B is x2 minus x1. Plus, give myself a little bit more room here. Plus, right, C. Well, C is just y2 minus y1 quantity squared. And then we take the square root of all of that to get A. So again, right, this bit right here, this is our B. This bit right here is our C. And this distance, which is the hypotenuse of the triangle, is our A. Okay. So just to recap that and clarify that, we can calculate the distance, or A, or the hypotenuse of the triangle, or error, depending on what we're talking about, is equal to the x-coordinate of the second point minus the x-coordinate of the first point squared, plus the y-coordinate of the second point minus the y-coordinate of the first point squared, and take the square root of everything. So hopefully you can see visually how we're able to go from this idea, let me slide over just a little bit, keep everything on screen here, right? How we can go from this idea of where a point should be versus where it ended up, the distance between them being the error, how we can take that, apply this abstract concept of Pythagorean's theorem, apply that to the coordinates from the coordinate system that we're projecting into to get the distance. And as always, if you have any questions, please reach out. Thank you.